This is the second part of a two-part lecture on the spectrum of modern IC choices. Although we are using an FPGA for this class, there are many other choices when you are designing embedded systems. In the last lecture, we talked about chips that were specified in the style of digital logic circuits. Now we're going to talk about stored program computers, which can be thought of as a very flexible and efficient way to implement an enormous variety of different functions with silicon. The next step on our spectrum are general-purpose processors. By design, these are capable of computing just about any function you can imagine, and do so with remarkably few transistors. But as always, there is a trade-off. Their extreme flexibility comes at a cost, primarily in speed, but also in energy consumption. Depending on the application, an implementation on a general-purpose processor can be many orders of magnitude slower and more power-hungry than, say, a full custom chip. I'm going to use Euclid's algorithm to illustrate coding for general-purpose processors. As usual, he probably didn't invent the algorithm that bears his name, but he was the first to publish it in a popular book, Elements, dating from about 300 BC. In this form of Euclid's algorithm, we compute the greatest common divisor of two numbers by repeatedly dividing them and taking the remainder. Things to look for include how the arguments m and n are passed, how the remainder is computed, and how the while loop is structured. This is Intel's 8386 processor. Released in 1985, this was the first 32-bit processor derived from the 8086 architecture made popular by the IBM PC. It remained the leading 32-bit processor architecture until AMD introduced its 64-bit extensions in 2003. Here's the programmer's model of the 386. It's built around four almost general-purpose registers that were once named A, B, C, and D, but first extended to 16 bits to become AX, BX, CX, and DX, then extended to 32 bits to become EAX, EBX, ECX, and EDX. The ESI and EDI registers are mostly intended for copying strings in memory. Intel's base pointer is what everyone else calls the frame pointer. Intel's instruction pointer is what everyone else calls the program counter. The 6-segment registers are a horrible idea left over from when it was a 16-bit processor trying to access more than 64 kilobytes of memory. On modern operating systems, they're all set to 0. Here's Euclid's algorithm in 386 assembly language. The first few instructions prepare the function for execution. First, it saves the base pointer on the stack. Then it remembers the current stack pointer as the base pointer and saves EBX on the stack. These two move instructions load the arguments m and n into registers EAX and ECX. The loop starts with CLTD and IDIVL, which together divides EAX by ECX and places the remainder in EDX, which is then saved in EBX. The testL instruction checks whether the remainder was non-zero, and the JNE sends control to L4 if it was. At L4, the former divisor n is moved to M, and the remainder is moved to n before the loop starts again. The last four instructions put the divisor n, which was in ECX, into EAX as the caller expects, restores the old value of EBX from the stack, uses leave to reverse the effect of saving the base pointer on the stack, and finally sends control back to the caller with ret, which pops the return address from the stack and jumps to it. The 386 is a so-called CISC, or complex instruction set computer, because its instructions can be complicated and in particular can operate on data in memory. In this example, leave is one such complex instruction. The rather irregular registers is also characteristic of CISC processors. This is Sun's Scalable Processor Architecture, or SPARC processor. Released in 1987, it was one of the most successful early RISC or reduced instruction set computer architectures. RISC processors have simpler instruction sets and more regular registers, and restrict memory operations to be load store only. The big advantage of RISC is that it enabled far more aggressive pipelining than the CISC chips of the day could achieve, which mean higher speeds with fewer transistors. Code density is one of the drawbacks of the RISC approach, which typically employs fixed width instructions, which on average are less dense than the variable length instructions of the CISC processors. Today, ARM is the leading RISC processor architecture, which added the thumb instruction set that uses 16-bit long instructions to help improve code density. Ironically, while Intel's processors present a CISC instruction set to the programmer, inside the processor, the CISC instructions are transformed into a RISC-like instruction stream that is executed on a deeply pipelined RISC-like ALU. So in some sense, both sides won. Here's the programmer's model of the SPARC. It's mostly just 32 32-bit registers. There's a program counter, a next program counter, and a status register that holds things like the carry bit and whether the processor is in supervisor mode or not. The rest are largely general purpose. Register 0 is special. It always returns a value of 0. Writing to it leaves it unchanged. This is surprisingly useful. For example, the SPARC does not have a register-to-register move instruction in hardware. Instead, the assembler translates a register-to-register move into a logical OR of the source register, the 0 register. General purpose register 14, by convention, is used as a stack pointer. Register 30 is used as the frame pointer, and register 31 is used as the function return address. The general purpose registers are divided into 4 groups of 8: global, output, local, and input. Instructions generally treat all registers identically. The 4 groups are treated differently by the SPARC's unique function call return mechanism. Like other RISC processors, the SPARC was designed to be programmed in high-level compiled languages like C instead of manually written assembly language. RISC designers recognized that programs make an enormous number of function calls, so it made sense to make them as efficient as possible. The limited irregular register sets of CISC processors made it difficult or impossible to pass function arguments via register. By contrast, RISC processors are designed to pass function arguments via register, and in no processor is this more obvious than it is in the SPARC. A SPARC processor actually has multiple overlapping groups of registers that operate as a stack. This is shown here. When a function is called, the so-called output registers become the new stack frame's input registers, and new local and output registers become visible. Naturally, the 8 global registers remain unchanged. By convention, output register 6 holds the stack pointer. When a function is called, the stack pointer becomes input register 6, which is treated as the frame pointer. Later, when the function returns, the stack-like nature of the registers restores the previous stack pointer. By design, taking a snapshot of the stack pointer and making it the frame pointer when a function is entered is exactly how it is done on most processors. On the SPARC, however, it's almost a minor side effect. Here's Euclid's algorithm compiled for the SPARC. One thing to notice is the compiler has unrolled the loop. While the original function only computes a remainder once, the compiled assembly appears to compute it twice. This avoids an additional branch, which is one of the more expensive instructions on the SPARC, although doing so here nearly doubled the size of the compiled program. To begin with, the save instruction advances the stack of register windows so the output registers into which the caller placed arguments, M and N, become the input registers for this code. It also exposes fresh sets of local and output registers. Save also creates the new value of the stack pointer by taking the old one and subtracting 96 to make space for 28 32-bit words. The next 3 instructions compute the remainder of arguments M and N. On display here is another of the SPARC's idiosyncrasies. The move instruction just after the call is executed before the call is actually performed. This was done to keep the instruction pipeline filled. The next instruction is always fetched before the previous instruction is decoded, and so rather than discarding what would otherwise be an unwanted instruction and wasting a machine cycle, the SPARC simply executes this instruction. Together, these 3 instructions copy input registers 0 and 1 to output registers 0 and 1, then send control to the .rem procedure that actually computes the remainder. The use of a subroutine to compute the remainder is another hallmark of RISC-like architectures. The SPARC designers, realizing that computing the remainder was such an infrequent operation that it would be faster on average to implement its relatively complex functionality as a subroutine rather than provide an explicit division instruction. By contrast, the 386 CISC processor has instructions for performing division, copying regions of memory, and other complex long-running operations that are implemented as subroutines on the SPARC. The rem function puts its result in register 0, which the next 3 instructions test for 0. Again, the delay instruction after the BE, the move instruction, moves N to register 0, which is where the caller expects the result to be. This isn't always necessary, but since the instruction is somehow hidden in the shadow of the branch, it only consumes otherwise unused time. I'll point out one other subtlety here. The comma A after the B and E means the delay instruction, here a move, will be annulled. That is, not executed if the branch is not taken. At the end, the ret instruction transfers control back to the caller, and because it's a control transfer instruction, its delay instruction is executed. Here, that delay instruction is restore, which pops the register stack and copies the I1 register, which holds N, into the result. That is, the caller's 0 register. The 386 and the SPARC represent 2 fairly distinct points on the general-purpose processor spectrum, but they have a common goal of running most workloads with similar efficiency. While that is a laudable goal for, say, a desktop computer or even a cell phone that will be expected to run many different kinds of applications, many processors and embedded systems will only ever run a single application. As such, it seems like you should be able to develop a far more streamlined processor that's only good at certain tasks and slow and awkward for others. This was exactly the idea that Motorola engineers and others had in the early 1980s. While digital signal processing had been done for many years by the 1980s, programmable processors at the time still weren't fast enough to run these applications. At the same time, the number of signal processing applications was growing quickly, and designers wanted to implement more complicated algorithms. So the time was right to develop new processors optimized for digital signal processing applications. Motorola, Texas Instruments, and others did this, and the fruits of their labor are probably in your pocket right now. Virtually every cell phone uses a digital signal processor, or DSP, to handle radio communication tasks, alongside one or more general-purpose processors that handle things like the user interface and other applications. This is one of those DSPs, the Motorola 56000. The programmer's model of the 56000 is highly irregular, even compared to that of the 3D6. To understand its design, it helps to understand a common DSP algorithm, specifically a finite impulse response, or FIR filter. The FIR algorithm, such as it is a simple convolution. It transforms an infinite stream of input samples into an infinite stream of output samples. Each output sample is the sum of the product of the last, say, 100 samples with 100 fixed coefficients that were chosen by the filter designer. Thus, an FIR amounts to 100 multiply and accumulate operations on sample coefficient pairs. The four 24-bit source registers are designed to store incoming samples and coefficients. The designers chose 24 bits because real-world signals are rarely any more precise. Two 56-bit accumulators form the center of the architecture. Their main use is to store and accumulate the results of multiplying a pair of source registers, although they can be used for other things. Incidentally, this is the only processor I know of that was named after the number of bits in its accumulator. The designers chose 56 bits based on algorithms like FIR. Multiplying a 24-bit sample with a 24-bit coefficient gives a 48-bit product. But if they had used a 48-bit accumulator, there would be an immediate danger of overflow, so they added 8 more bits to make 56. As a result, you don't have to worry about overflow until you accumulate more than 256 products. There are 8 groups of address registers, which are quite powerful in the 56000. They directly support wraparound buffers. Each group of 3 registers holds an address, the size of a buffer, and a stride that controls how quickly a program steps through the buffer. On the right are miscellaneous registers, including a conventional program counter and status registers. In addition to conventional conditional branch instructions, the 56000 supports so-called zero overhead loops controlled by loop address and count registers. Together, these can repeat a block of code without using count or branch instructions. Unusually, the 56000 stack resides on chip in the form of 16 paired registers that save program counter and status register values. This is used for function calls, interrupts, and nested loops. Here's the 56000's main data path, which is primarily a pipeline for performing multiply-accumulate operations. At the top are 2 data buses from the 56000's 3 memory regions. Each memory is 24 bits wide, and all 3 can be accessed simultaneously. The X and Y regions are meant to store samples and coefficients. The third region, called P, holds instructions. The 4 source registers take data from the X and Y buses, typically a sample and a coefficient. 2 source registers feed their contents to the multiplier, which produces a 48-bit result. The product from the multiplier is passed to the accumulator and rounding unit, which adds the contents of one of the 56-bit accumulators to the product from the multiplier. Finally, the shifter limiter can transform a 56-bit accumulator value into a 24-bit value that can be written back to memory through either the X or Y buses. Here's the address generation unit of the 56000. It consists of 2 identical address ALUs designed to generate 2 addresses per cycle, one for the sample memory, the other for coefficient memory. The address registers are split into 2 groups, one per ALU. In each cycle, 2 addresses can be read from the R registers and updated with the 2 ALUs. An update can add 1, subtract 1, or add an offset or N register to the given address. All of this arithmetic can be done modulo a value in a modifier or M register to implement circular buffers. Finally, the ALUs have the unusual ability to also operate in reverse carry mode, a core operation in performing the fast Fourier transformation algorithm, and about the most digital signal processing specific feature of the 56000. Here, more or less, is the program that the 56000 was designed to run efficiently, a finite impulse response filter. The first 4 instructions load constants into address registers. R0 holds the base address of an array of samples, R4 is the start of the coefficient array. And both M0 and M4 are set to 1 less the length of these arrays so that R0 and R4 will wrap around at the end of these arrays. The MoveP instruction reads the next input sample from a peripheral in Y memory and writes it into the sample array in X memory. The clear instruction clears the accumulator A and primes the pipeline by reading the first sample from X memory into register X0 and the first coefficient into Y0. All 3 things happen in parallel in a single cycle. The rep instruction implements a zero overhead loop. It causes the processor to execute the instruction following it, here a MAC instruction, n-1 times. Repeating a single instruction wouldn't be very interesting on most processors because it wouldn't do much, but not on the 56000. This MAC instruction does 6 things. Multiply the sample and coefficient in register X0 and Y0. Add the product to accumulator A. load the next sample into x0, load the next coefficient into y0, increment the sample address in R0, wrapping around if necessary, and incrementing the coefficient address in R4, which may also wrap around. This is all pipelined, so when the multiplier is multiplying one sample coefficient pair, the next pair is being loaded from memory. Similarly, the addresses are updated only after the loads take place. The result is that when the rep loop is completed, the last sample coefficient pair remains in x0 and y0. The MAC-R instruction multiplies and accumulates this last pair, rounds the result, and backs up the sample pointer in R0 by 1 so that the next sample is stored just before the one that was read at the beginning of the loop. Finally, the MOVP instruction writes the result to a peripheral address in the Y memory called output. The 56000 is an efficient processor architecture for DSP applications, but it's a difficult target for a C compiler. TI's contemporary and more successful TMS 32010 presented a similar challenge. DSP users who were tired of coding in assembly language wanted a change. In 1997, TI introduced the TMS 320 C6000 line of DSPs. This new processor architecture was designed as a suitable target for optimizing C compilers. The C6000 employs a very long instruction word or VLIW architecture, which couples a RISC-like general-purpose register file with multiple parallel functional units. These functional units operate in lockstep, controlled by a single instruction stream of wide instruction words. A word consists of one RISC-like instruction for each functional unit. Here's a block diagram of the main data path of the C6000, which consists of a pair of 16-entry 32-bit register files coupled to two groups of 4 functional units. For the most part, each register file serves its group of functional units, but a limited amount of communication between the two groups is allowed. The 4 types of functional units have different capabilities. The L units can perform 40-bit arithmetic and logical operations. The S units can perform 32-bit arithmetic shifts and perform branches. The M units can perform multiplication, and the D units can perform loads and stores and address arithmetic. These register files are impressive. They have 9 read ports and 5 write ports. It's costly to implement a register file with so many ports, and the die photo bears this out. A single register file consumes almost as much area as 4 functional units. Here's the inner loop of the FIR algorithm expressed in C6000 assembly. Its functionality corresponds to that of the MAC instruction we saw in the 56000 FIR code. It fetches sample coefficient pairs, multiplies them, and accumulates the result. This single very long instruction is built from 6 instructions that run in parallel, indicated by vertical bars. Each line contains a single RISC-like instruction with an opcode such as LDH, which loads a half-word from memory. Each instruction is labeled with the functional unit it should use. Since this first instruction fetches a sample from memory into the A2 register, it needs to run on the D1 unit. The D units can also do address arithmetic. The assembly is using C-like notation that indicates register A1 supplies the address and is incremented after the data is fetched. The second LDH instruction simultaneously loads the next coefficient from memory into register B2 and increments the pointer in B1. The MPY instruction multiplies the sample in A2 and coefficient in B2 and stores the result in A3. Unit M1 has direct access to registers A2 and A3, but because B2 is in the other register file, this instruction needs to access one of its operands through the shared cross-register file path, as indicated by the X. Only one such transfer is allowed in each direction per cycle. In conventional architectures, the program counter and conditional branch instructions are used to control which instructions are actually executed. While the C6000 can also use this technique to control which instructions are executed, its parallel instructions coupled with its very deep pipeline can make branching slow and awkward. To help this, the C6000 permits predicated instructions, a technique common in VLIW processors. Any instruction for a functional unit can be made to execute only if a certain condition is true, such as whether the B0 register is non-zero. If the condition is false, the functional unit effectively executes a no-op instruction. In this code, a predicated branch instruction controls the number of iterations in the loop. The branch instruction runs only if register B0, which is being used as a loop counter, is non-zero. As a result, this instruction executes as many times as the count in B0, which is updated by the sub instruction. The VLIW approach was briefly popular among computer architects in the 1990s, but didn't stay around long. Its basic failing is its insistence on a single program counter. It turns out to be very difficult for a compiler to find and exploit the kind of instruction-level parallelism required by a VLIW architecture, even for signal processing applications which tend to have simple control flow. Processor architects have instead built processors that attempt to derive such instruction-level parallelism dynamically, sometimes even from multiple instruction streams via simultaneous multithreading. But the path of least resistance has turned out to be multi-core processors, which provide a more traditional multi-threaded form of parallelism at the expense of shared memory coherency issues. The ASICs and FPGAs from the previous lecture were specified as digital logic circuits, a net list of gates and flip-flops driven by a clock. By contrast, the processors we have been talking about, including general and special purpose, are fundamentally stored program computers and that their behavior is customized by giving them a sequence of instructions to execute. A third group of chips perform computation and are configured through software, but do not accept programs. Instead, these chips are controlled through command and status registers, something like buttons and lights that can be set and read from software. Here is an example of what would appear to be a simple sensor chip that falls into this category. This is the block diagram for the analog device's ADXL 345 3-axis accelerometer, which is present on the DE1 SoC. This chip is built around a sensor made from surface micromachined polysilicon. This tiny structure deflects in response to gravity or other acceleration, which changes its capacitance and generates a signal that's proportional to the acceleration. The signal is amplified, passed through an analog to digital converter, low-pass filtered, and then fed to an interface that allows the data to be read by a host processor through a serial I2C bus. The chip itself is tiny, only 3 by 5 millimeters, and only has 14 pins. The first thing to ask about a chip like this is how it communicates with its environment. Most chips have an interface designed to work with a processor, and the ADXL 345 is no exception. It supports 2 low-speed serial protocols, SPI and I2C. On the DE1 SoC board, the ADXL 345 is connected to one of the 2 I2C controllers in the HPS of the FPGA, so the accelerometer can be controlled through Linux. From the ADXL 345 datasheet, here is an I2C timing diagram. The I2C protocol is simple enough that you could build your own bus controller, but is also common enough that there are many existing controllers that you can simply use. Chips like this may also have parallel bus-oriented protocols designed to be connected directly to a processor. Simpler raw protocols designed to interface directly to other digital hardware without the need for a processor, or a combination of these. Here is the real challenge with any of these chips. This is a list of the 30 8-bit registers within the ADXL 345. Some registers are read-only, such as the 6 that report the output data for each of the 3 axes. The remaining registers can be both read and written, and largely configure how the device operates. For example, the ADXL 345 has a mode where it can report a tap, a sudden small acceleration. At least 8 registers control this feature and allow the user to tune parameters such as the minimum magnitude of a tap, its minimum duration, how long before a double tap can begin, which axes are monitored for a tap, and so forth. Other registers control the range of accelerations that the device can measure, various offset values, the format of the data returned, the operation mode of the data FIFO, various power-saving modes, and so on. The data sheet for the ADXL 345 is a scant 36 pages. There are only 3 pages of detailed documentation of the registers. This is because the ADXL 345 is a comparatively simple chip, with few operating modes and essentially a single function. By contrast, here's the block diagram for the analog device's ADV7180 standard definition video decoder. This chip digitizes standard definition analog NTSC PAL or CCAM video into a digital bit stream that can be then displayed, compressed, or otherwise manipulated. Like the accelerometer, it is primarily an analog to digital converter followed by a digital processing block. It also uses an I2C bus interface for configuration, but because video is a high bandwidth signal, it transmits its data through a clocked high-speed 8-bit parallel interface with separate horizontal and vertical synchronization signals. Here is merely a partial list of the hundreds of registers inside the ADV7180. These control things, such as the video input source and format, the output format, settings for closed captioning and teletext, and countless filter parameters. It's remarkable how many different things this chip is able to do, but its flexibility comes at a price. Its basic documentation is 112 pages long, including 25 pages of tables mostly describing the encoding of the various registers. The explanation of what these registers are actually doing, such as settings for the NTSC comb filter for minimizing color artifacts, sprawls across the rest of the documentation. Finally, we come to the simplest chips I know of, fixed function chips. Such chips contain small logic circuits, such as the 7400, which contains just 4 logical NAND gates, and the 74374, which contains 8 flip-flops connected to a common clock with a single output enable. You don't get to control much with these chips, just which part number you're buying. You don't get to choose the layout, circuit, program, or configuration of these chips. But for many years, such chips were all that were available. These 2 chips are from the so-called 7400 series, which TI and others have produced since 1964. There are now a few hundred different 7400 series chips. They never got much more complicated than this. The original TTL circuits, or transistor-transistor logic that these chips were implemented with, has long been obsolete, although you can still buy chips from this family today for repairing older equipment. Today, this family is implemented in over 30 different logic families, with different power consumption, speed, and voltage levels. Here's the schematic for one of the more complicated TTL chips, the 74181 4-bit ALU slice. It can add, subtract, and compute logical operations on two 4-bit inputs and produce a 4-bit result. Here's a die photo of the 181 taken by Ken Shirriff. The obvious advantage of these chips is their simplicity, meaning they can be produced affordably long before processors or other much more complicated integrated circuits. Starting in the 1960s and going all the way to the 1980s, mini computers and others were implemented using chips like this. Today they are still widely available, but they're oddly expensive for what they do. Today, a typical 7400 series chip costs between 10 cents and $1, which is surprising since that's about the same price they were in the 1980s. While that's not a lot of money, it's a lot of money for a few hundred transistors. So what happened to Moore's Law here? Actually, Moore's Law explains exactly why these chips are no longer economic. Moore's Law observes the number of transistors on a die that minimizes per transistor cost has been growing exponentially since the 1960s. These chips are just too simple to be economic. Their per transistor cost is swamped by their packaging, distribution, and other per chip, not per transistor costs. You've already experienced a similar change in your lifetime. You'll be able to brag to your kids that at one point you could buy just 4 processors at a time, just like I can brag to my kids that I once bought just 4 NAND gates.